So we could do QCD, okay, but then I can only show you numerical results, okay, and so people have done this in the past for QCD, for scalars, for all kinds of different approximations, okay, and since the result is always structurally similar if you do this, okay, I'm going to show you the easiest possible thing one can do, which is the so-called relaxation time approximation. Okay, and I'll call this RT, or I'll abbreviate this as RTA, okay, where essentially one says, okay, what is the effect of these collisions? So essentially when these particles interact, what do these interactions do? Well, these interactions somehow try to restore equilibrium of the system, so try to bring the phase-space distribution to its equilibrium form, which, let's say, for a gas of bosons would be the Bose-Einstein distribution, okay? And what you say in the relaxation time approximation is, you say, well, the only effect that this collision integral has actually is to somehow drive you towards this equilibrium on some time scale that I call the relaxation time, okay? So if you do this, so in this case, the collision integral in RTA, okay, is just given by, I write down a relaxation of the distribution to its equilibrium, okay, and so you see this is not, so this is energy times the time derivative essentially. So if I consider this in the rest frame, then I can write this factor P mu U mu up here, right? So this basically gives you another factor of energy in the rest frame, and then the time scale on which this relaxation happens is called the relaxation time. So tau R is the relaxation time of the system. Okay, so now this looks very simple, okay, because this actually looks like it's a linear equation now in F, okay, but as a matter of fact, it's not, okay, and the reason it's not is that I have to be a little bit careful about somehow how this equilibrium is specified, right? Because I mean, the equilibrium distribution will look different for different systems, right? Say, for instance, consider a system that is moving at a collective velocity, then, you know, the corresponding equilibrium system will also be moving at that collective velocity. Or if one system is hotter than the others, right, or contains more energy, then they will also correspond to different equilibrium states. Okay, so what one also has to do is one has to determine this equilibrium state, okay? So this F equilibrium, okay, is the equilibrium distribution. Okay, and so for instance, if you were to consider bosons, right, so if you were to have bosons, then this is nothing than the Bose-Einstein distribution. So in that case, F equilibrium would just be the Bose-Einstein distribution, and the Bose-Einstein distribution depends on the energy of the particle, but now it's the energy measured in the local rest frame. So it's P mu U mu. That's the energy in the rest frame of the system, okay, locally, yeah, and then the temperature, okay, and so in principle, so this depends on X and P because these local velocities and temperatures can be different at different points in space and time. So my system can have more energy here than here, right? Then this would equilibrate to a different temperature than this spot over here. Good. So this specifies somehow this equilibrium distribution up to one thing, okay? Namely, I still have to provide a description for how to compute here this rest frame velocity. Yeah, so how to compute essentially in what frame my system will equilibrate, right? So that's a similar question like this frame choice question that we discussed in the context of hydrodynamics, and to what temperature the system will equilibrate, okay? And yeah, there's a question. I mean, this is just the rate at which the system relaxes to equilibrium. And essentially what I'm saying is, so there's a simplification here that you're saying that all possible deviations from equilibrium, right, will relax with the same speed towards equilibrium. So it doesn't matter whether, I don't know, I do a high energy perturbation of my system or a low energy perturbation or anything. Everything will just decay at the same rate. Yeah. Okay. You mean with P mu U mu? Yes, that's true, actually. So I should probably put a plus here. Yes, you're right. You're right. Okay. Good. Thanks for pointing this out. Okay. So what we still need to find is we still need to have a prescription for how to determine the the frame in which the system will equilibrate and the temperature at which it will equilibrate, okay? And so this is in a sense where this nonlinearity comes in, okay? So these guys can be determined actually, or in this case have to be determined, okay, from the energy momentum tensor of the system, okay? And so let's write this down, okay? So with u mu x and t of x determined from a matching condition, okay? And it turns out that in this case, you actually have to adopt the Landau matching condition, okay, in order to satisfy energy momentum conservation. So we learned in the discussion of hydrodynamics, it's not a good idea to use Landau, the Landau frame or Landau matching. In this case, if you're doing here the microscopic description in kinetic theory, it's the only thing you can do, okay? Otherwise, your collision integral does not conserve energy and momentum for this kind of just constant relaxation time for every rate. Yeah. Okay, so so this is determined by Landau matching. Okay, so this we already wrote down. So it's the solution of the eigenvalue equation. Okay, minus E u mu. Okay, where in this case, so this would give you the energy density of the system, okay, and if we're considering an equilibrium system of bosons, then from the energy density you can get the temperature by just usual thermodynamics. So for non-interacting massless bosons, this would be pi squared over 13 u times t to the 4. So by solving this, so by calculating the energy momentum tensor for a given f, right, according to this up here, you get the energy momentum tensor. Then you solve this eigenvalue equation. You get the eigenvector, the time-like one, and the eigenvalue, and from the eigenvalue you can then determine the temperature. And so once you know this, then you know where the place that your system will relax to. Okay, and as I said, this is somehow necessary to satisfy energy momentum conservation. Okay. If you make the relaxation time, for instance, momentum dependent, then this matching condition takes a different form actually, and then you have to be more careful. Okay, but in the simple case, this is what you have to do. Good. Now the other thing that that we can look at is, or the other thing that we should talk about a little bit more is what is the role of this relaxation time. And somehow this is, I mean, this is, yeah? Between this and the lattice result, well, that's what I said, right? I mean, if you choose this to be 40, okay, you get a reasonable description of high temperature QCD, okay? Yeah. And then to asymptotic temperatures, it goes from 40 to 47.5, I think. Yeah. So it's okay-ish, but it's also not fantastic, okay? So above, I think, roughly 2 times TC or so. Yeah. Okay. Now I lost track of what, yeah. So the last thing we should talk about is now this relaxation time, okay? So this relaxation time, if I just write it, is a time scale, okay? So I'm introducing a time scale here, okay? Now, in principle, this timescale determines how quickly my system moves towards equilibrium, right? And we had, so if we, for instance, look at analogous things up here in hydrodynamics, okay, we had other coefficients, transport coefficients, okay, which also gave us information on this, right? So, for instance, this coefficient tau pi, okay, which is actually second order transport coefficient, so that's something you can calculate in any theory, okay, also tells us about about how quickly a system relaxes to equilibrium, okay, and so if we take such a system of massless bosons, okay, and we calculate now these transport coefficients, indeed, it turns out that, okay, so for a conformal system, okay, you can choose, so for a conformal system, the relaxation time, okay, should not be some constant or some time scale that you introduce, but it should depend on the natural scales of the system. Now there's only one scale for an equilibrium system. This would be the temperature, okay? So on dimensional grounds, this should be inversely proportional to the temperature, okay? And it turns out that the proportionality constant is just what gives you the viscosity, okay? So this relaxation time is actually 5 times the viscosity divided by the temperature, 5 eta over s divided by the temperature, okay? And actually, if you compute this second order transport coefficients tau pi, okay, that turns out to be exactly equal to the relaxation time. Good. For conformal system. Yeah. Yeah. So really at this level, what this means is I take massless particles, okay? I make them to be bosons, and I do this particular choice for the relaxation time. Yeah. Okay, that's what I have to do, then I get these results. Okay, good. So this is the theory we now want to look at. Okay, so let us start to adapt this description to the problem that we're interested in. Okay. And the problem that we're interested in is, well, it's still sketched up there, okay? So is what now happens to the system in Bjorken flow, okay? So, so now consider Bjorken flow. Whoop. Or actually what we're going to consider is this generalized Bjorken flow where we keep generalized Bjorken flow, okay, where we keep our scale factor to be anything, okay? And what we want to compute is the time evolution. So we adapt the Bjorken symmetries, right? So our system does not depend on transverse coordinates, and it's also translation invariant in rapidity, okay? And then really what we want to compute is the longitudinal pressure as a function of time, okay, which is nothing than this T eta eta component of the energy momentum tensor, okay, and so we can plug this in right away, okay. So what we get is now we have to see what this integral over these different momenta actually is, okay. So we have an integral over the transverse momenta, d2p perp over 2 pi squared, okay. Then this third factor in the integral, okay, is actually an integral over p upper eta, okay, so this has another index, okay, and also so this has another dimension also, right? We said that, okay, right, and when we're in this co-moving coordinates, then the dimension of these objects is different depending on whether I lower or raise the matrix, okay. This metric determinant is just the scale factor, okay, and now if we look at T eta eta, okay, then what we get is we get 1 power of the upper p eta and 1 power of the lower p eta. So we have to once lower this, okay. Lowering just is multiplication with the metric factor that was a squared, okay. So what we get then is p eta a of tau squared p eta, and divided by the energy. Okay, so that's just given by the on-shell condition. I'm not going to write this down. And then our phase space distribution depends on proper time, transverse momentum, and our longitudinal momentum. Okay. So now we can have a look at this. Okay. And so what we start to see here is that if we actually have a closer look, okay, then this p eta always seems to come with 1 power of the scale factor. Okay, so in principle it's always p eta times a that appears here in this description. Okay, and indeed it turns out that this is somehow the more physical variable to look at. Yeah, because well, we already learned. Okay, so we already learned something that if I upper and lower one index of the longitudinal ones, right, then that has the same dimensions as transverse things, okay? And so if I look at this, then this would be indeed something like a of t squared times p upper eta squared, okay? And now basically we just want to call a times p some different name, and we're going to call this p longitudinal, okay? So p longitudinal we define as a of tau times p upper eta, okay? And then this we can really think of sort of a physical longitudinal momentum, okay, in the co-moving rest frame of our system, okay? So this is the physical momentum in the co-moving frame, okay? And so then if we evaluate now again what our pressure is, okay, then this of course becomes very simple, right? So we change the integral measure, and this just becomes an integral over p longitudinal, okay? And then we have here p longitudinal squared over EP, okay? Multiplying our phase space distribution, okay? Which I can either write in terms of p eta or p longitudinal as I want to, okay? So let's make it depend on p longitudinal, okay? And in this case, the on-shell condition is just that the energy of a massless particle is given by the square root of transverse momentum squared plus longitudinal momentum squared. So there's no more metric factors also appearing in here, okay? So that's why really this looks like now a physical longitudinal momentum. Good. So that's the guy we want to calculate, okay, at the end of the day. Now, in order to calculate this, we need to solve the Boltzmann equation, okay? And so for this, we have to work out one more term, namely what this expansion does, okay? And actually, this is also the only thing we'll really be able to solve, okay? So if you look back up at this cartoon here, right, then, you know, I mean, why are we doing this? Why are we not just using Hydro? Well, we're doing this because we're mainly caring about this expansion-driven regime, right? Yeah? So we already know that at later times where interactions are important, they are, you know, we expect hydrodynamics to emerge, okay? And so in principle, we're happy with this, but we particularly care about what is the physics here of this that is going on at early times, okay? So now we have to evaluate Boltzmann equation, okay? So now evaluate our Boltzmann transport equation, okay? And so essentially we have to evaluate what these curvature terms do, right? So we had this term Christoffel symbols, p mu, okay? df, dpi, okay? So now we worked out all the Christoffel symbols, okay? And we found the only ones that are non-zero are the ones which involve eta and tau, okay? Now here, because the phase space distribution only depends on the spatial momenta, because we've already gone on shell, the only thing that we can pick up is eta, okay? So what we get is we get gamma eta tau eta, okay, plus gamma eta eta tau, okay? And then here I get p eta p tau, okay? So these are actually the same, okay, times df dp eta, okay, and these Christoffel symbols were just a dot over a, okay, so this just becomes out to be 2a dot over a, p tau, which is the energy p eta df dp eta. Good. Okay, so this is what somehow this expanding space-time does to us. Okay. Now, here's a step where one has to be a little bit careful. Okay. Because, okay, we can always work with this p eta, but we just argued that somehow the more physical thing to look at is actually this p longitudinal, so the physical momentum in the co-moving frame. Okay. Now, the thing is, when I write down the Boltzmann equation and I take partial derivatives, let's say a partial time derivative, okay, a partial derivative is always a derivative where you're keeping something else constant, okay, and what you're keeping constant are the momentum coordinates, okay. So if you want to change to using this here, this p longitudinal, okay, you have to work out that also the partial derivative changes, okay. So we need another identity before we can really write down the form of the Boltzmann equation now in this Birkenflow. So if we look at the derivative of the phase space distribution at some constant p eta, and that's what appears in the form of the Boltzmann equation like I wrote it down, okay, I can translate this into a derivative at constant p longitudinal, but I have to take into account that the relation between p eta and p longitudinal changes at the same time. Okay, so you can work this out. Okay, so this is a derivative at constant p longitudinal. Okay, but then you get one extra term, which is the change of p longitudinal with respect to tau at constant p eta. Okay, plus the derivative of f with respect to p longitudinal at constant time. Okay. And this is not very difficult, right? P longitudinal is a times p eta, okay? So if you take a time derivative, you get an a dot times the p longitudinal, so this you can, times the p eta, so this you can write as a dot over a times p longitudinal df dp longitudinal, the second term, and then, then of course you keep the first term, which is df d tau at constant p longitudinal. Okay? And so now, if you stick this into the Boltzmann equation, okay, then in principle this was somehow, we had p mu d mu, so there's this term appearing. This one came with a minus sign, okay? Now, this change of variable terms that we get is exactly the same. But if we also multiply this with a p mu, so with a p tau, then it's exactly the same term as we're getting here. I mean, p longitudinal dp longitudinal, I can write as p eta dp eta, I can write as p longitudinal dp longitudinal, right? That's just at constant times, that's just a rescaling, okay? So this term kills one of these guys that you get up here at the end. Good, so, okay, so collecting everything now, this is what we want to calculate, okay? These are the intermediate steps. So now let's write down what we get, okay? Okay, so if we collect everything, okay, then we can divide by 1 power of the energy. So this p tau d tau just becomes d tau. So we get the time derivative of f, and then we bring all other terms over to the right-hand side. So we remain with 1 power of exactly this form, namely a dot over a times this. And this now has a plus sign, sorry, a dot over a, okay, p longitudinal, and I'll write it like this, df dp longitudinal, okay? So this is purely the effect of the expansion, okay? And then in principle, the other term we have is the collision integral, and this would be divided by p tau, okay? So divided by my energy, okay? So if we work this out, now we can make this more concrete, okay? If we say we actually stick in the collision integral for RTA, okay, and we adapt this situation to Bjorken flow, okay. So if we do that, okay, what do we get? What we get is A dot over A is just 1 over tau, okay, and then we have P longitudinal dF dP longitudinal, okay, and then we have here minus 1 over tau r, okay, F minus F equilibrium. So this P dot U factor is just, U is time-like vector, right? So this just cancels exactly this energy, and then we get this. Good. So now we can actually make an interesting observation, okay? So we see now kind of precisely the same pattern that we observed already for the Israel-Stewart solution, okay? Namely that in principle there's somehow two time scales appearing here in this equation, right? So the one is related to, why is this actually not right pink? Very good. So one is related here to this expansion rate. So this is this 1 over tau, okay? And that is what is very, very dominant at this very early times, okay? So the other factor is then here related to the relaxation time of the system, okay? And so if we now start solving this at a given point in time, okay, what will happen will essentially depend on whether tau over tau r is small, okay? So then we're at early times and we're in an expansion dominated regime. Whereas if tau over tau r is large, okay, then the expansion is weak and we're kind of just dominated by this term that drives us, by the interactions that drive us towards equilibrium, okay? And so we really see kind of how we have this different things here. Okay, so what we are, okay, so what we are now primarily after is understand what happens, understand better if we deal with this microscopically, what happens here at early times, okay? So, and okay, I mean, if our times are really small compared to the equilibrium, to this relaxation time, okay, then we may just neglect this altogether, okay? So what we can try to do is we can basically, similar like we did this for Israel-Stewart, we can try to solve this perturbatively, okay, in expanding around early times, so in expanding in somehow in powers of tau over tau r, okay? So what we can do is we can neglect interactions for tau much smaller than tau r, okay? And this then results in a simple equation, okay, that is really linear, okay? So if we just kick out this term and we work this out, okay, it's my usual mistake, okay? Then what do we have? Then we just have d tau f, okay? Which now, the way we wrote it depends on tau, transverse momentum, and longitudinal momentum, okay? Is given by A dot over A, okay? And then we just have here the normal derivative term, the normal derivative with respect to P longitudinal, okay, of our distribution, which depends on tau, P perp, and P longitudinal. Good. So this is now, so now if you look at this equation, okay, this is a, I mean, this is now a linear partial differential equation of first order, okay, and this you can always solve. Do you know how to do it? Is it? No? Yeah? Yeah, so you can always solve this by methods of characteristics, which is, so methods of characteristics is kind of like, so in the simplest case, you can imagine this, you follow kind of the, what an individual particle does, so to say, right, and solve for, so you cast this partial differential equation into evolution equations for the time evolution of momentum and positions of individual particles, okay? So you can always solve this by method of characteristics, okay? I'm just going to write you down the solution and we'll convince ourselves that this is correct, okay? Okay. You can also kind of get this from physics. Okay. You can also think. Okay. Thinking is always a good idea. Okay. So if you think, we already said, okay, what does this term describe? What it somehow describes is the redshift of momentum due to longitudinal expansion. Okay. And so if that's the only physics effect I'm taking into account, right, then all that should happen is that my particles that I put there, okay, just their momentum gets redshifted, their longitudinal one, right? And that should be the full solution, okay? And so indeed, that's what you find. Okay, so let's have a look. Okay, so the solution is very simple. Okay, so if I look at my distribution as a function of time, transverse and longitudinal momentum at some given time, okay, and I want to relate this to what I had at an earlier time, okay, that I'm going to call tau naught, okay, then in principle, nothing happens here to the transverse momenta of my particles, okay, they stay untouched by this whole equation, so we get the same dependence on the transverse momentum, okay, but our longitudinal momenta, they encounter this redshift, okay, so what we get is that the longitudinal momentum gets multiplied by the ratio of the scale factors between the time that we are looking at the system, okay, compared to the initial time, okay, and so now you can see, right, so that's, if you take the time derivative, okay, then, well, you actually take a derivative of this component, then you take the interior derivative, so you get your A dot, okay, and if you were to just take a longitudinal momentum derivative, so a derivative with respect to this last component, okay, then you would instead get P longitudinal A, okay, so if you plug this in, you can verify that this is the solution. Okay, now what is the physics of this solution? Okay, so let's really think, okay. So the physics of this solution is that my longitudinal momenta, okay, somehow get smaller, okay, so that they get redshifted because I'm in this expanding geometry. You can also, by the way, you can also look at this sort of not in the co-moving geometry where you encounter this redshift, but you can also think that you're looking in Minkowski space, okay, and what happens then is you're sort of looking at a slab in the middle, yeah, and if a particle was moving really fast longitudinally, it would just fly out of the slab that you're looking, okay, so that's why whatever stays in the middle is slower, okay, because the stuff that was fast sort of escaped the region that you're actually interested in. Yeah. Okay, so the properties of the solution are like this. So if we draw a sketch of our phase space distribution as a function of transverse and longitudinal momenta, okay, then let's say at some initial time we have some distribution which has a certain form, okay, so let's say it extends to some characteristic momentum scale q in the longitudinal direction, okay, for instance after there could be an exponential decay or something like this, okay, and then if you go to later times, so tau larger than tau naught, okay, then in principle the shape of the transverse distribution stays exactly the same. Okay, this is not a good cartoon. Okay, so good. So transverse shape stays exactly the same, but this distribution gets squeezed by the ratio of scale factors. So here you would have somehow the typical support of this distribution would be then q times a of tau naught over a of tau, right? Because if you plug this in, then you again evaluate this at the same scale, q. Yeah? So kind of the factor is inverted here when you actually plot it. Yeah? Okay, so now what does this mean? So now what does this mean for our evolution of the pressure? Okay, so that's at the end of the day what we are really after. Okay, and in principle, okay, this is now unfortunate. Okay, so in principle, we see how the pressure is calculated. Okay, the pressure is the second moment with respect to the longitudinal momentum of this distribution. Okay, so now let's say initially I set this up, okay? So I set this up with some pressure. Then what happens is that after some time, this distribution gets squeezed and squeezed, okay? So what happens with the pressure? Goes down, okay. Where does it go if I just keep solving and solving? It goes to 0, okay? Because one thing I didn't tell you yet, but that is fairly obvious, okay? This phase-based distribution of quasi-particles is a positive definite quantity, okay? So this is counting how many particles I have per unit volume, per unit momentum, so that has to be positive, okay? All these factors in here are positive, so the minimal value that this pressure can take is actually 0, okay? And so what is happening here now is that due to this expansion, our momenta encounter this redshift, the distribution gets squeezed and squeezed, okay? And thereby very rapidly approaches 0, okay? We can also, so this is kind of the intuitive thing that we come to realize here, okay? We can also sort of argue this a little bit more mathematically, okay? Let's maybe do that, okay? So we can approximately compute this integral, okay? And this will also tell us about a little bit more about how the pressure goes down, okay? So let's have a look, okay? So let's try to stick this solution in, okay? So what do we have to calculate? So we have nu integral d2p perp over 2 pi squared, okay? Integral dp longitudinal over 2 pi, okay? P longitudinal squared over the energy, and the energy is now square root of p perp squared plus p longitudinal squared, okay? And then if we do this concretely for Bjorken flow, where we have this expansion rate 1 over tau, right? Then this ratio of scale factors is just tau over tau naught. So we would have the distribution as tau naught, okay? So this is the solution I'm sticking in here, p perp and p longitudinal times tau over tau naught, okay? And so basically, the idea is now to undo this here, okay? So now to introduce a new integration variable, so substitute, okay, p naught longitudinal, which is p longitudinal times tau over tau naught everywhere, okay? And basically in doing this, okay, we then get to integrate always over the same argument, okay? But here we have to then introduce these factors tau over tau naught and tau over tau naught squared, which we can pull out of the integral, okay? So we get something like tau naught over tau cubed, okay? Then degeneracy factor integral over 2 pi squared, integral dp longitudinal at time 0 over 2 pi, okay? Then this is p0 longitudinal squared, okay? Now, the only place where this doesn't work in principle is in this energy denominator, okay? So there we have p perp squared plus, and so now we have to really insert this, okay? So plus tau naught over tau p longitudinal squared, okay? And then we have this initial distribution which depends on tau naught, p perp, and p longitudinal, okay? But now if we go to times which are much larger than tau naught, then the fact that we have this kind of little addition here of some longitudinal momentum doesn't really play a role, okay? So we can just approximate this by pt basically, okay? And so what we then find is that this goes as tau naught over tau cubed, okay, times some constant which comes from the initial condition, okay? So then this no longer has a time dependence. The time dependence eventually goes away, okay? And so what we can conclude from this analysis now is if we look at the evolution of the pressure, okay, then we find a power law relaxation. So let's just some constant. Then we get a power law relaxation towards zero pressure at very, very early times, okay? Yeah. Now, there's this tau naught there, which is kind of saying like, okay, when do I start to actually describe the evolution of my system, okay? And now you can argue in different ways, okay? In principle, the way we set this up, we said we want to really start sort of as early as possible after the collision, right? Really take the outcome that is there and then start to describe its evolution, okay? It turns out there's something like a formation time, so you need to wait at least some time, okay, before you can think of your system possibly as interacting particles, okay, even in a weakly coupled theory, okay? So there's sort of a lower limit to this, okay, and that's maybe where you should start this, okay, but then very rapidly, essentially, any kind of pressure you could possibly have would decay. So actually, the only natural choice for your initial conditions is actually also something which at early times has a vanishing longitudinal pressure. Yeah. Okay, so let's now look at the evolution of the pressure, really, what it looks like. So evolution of the pressure, okay? So what we find is that, and this we have shown, is really there's an early time attractor, okay, where our longitudinal pressure just goes to 0, okay, and there's a power law relaxation to this attractor, okay, which is solely due to the expansion, okay? And so, in principle, if I now were to develop this at early times, right, then the sort of the fixed point solution would take the form that it's 0, and then come the corrections due to interaction, okay? So the first corrections would then be of order tau over tau r. So that's what we dropped here all together, right? But that's in principle the first kind of corrections you could get. Okay, now, so with this, okay, we can now look at sort of what would be the evolution of, and I'm going to just do pressure over energy density here as usual, okay? And we're going to look at tau over tau r, which is basically very similar to W tilde, okay? Because tau r is the inverse of the temperature divided by times eta over s. So this is T tau r divided by 5 eta over s. So usually we put a 4 pi there, okay? But it's in principle the same, okay? So at early times, we have this being 0, okay? And we're bound to positive values, but every kind of finite pressure we would put here would exhibit a power law relaxation to this 0 pressure attractor, okay? Now, we can ask what happens at late times, okay? Well, in principle, we could now do this the other way around, right? So you could now start to expand around dominance of the interaction term. So neglecting first the expansion, okay? Well, if you neglect that, what you would find is that you would basically just say, okay, my system is in equilibrium, and you would actually get ideal hydrodynamics in that case. So if you expand for the dominance of interaction, essentially that's a way of deriving hydrodynamics, okay? That's how this was, how this is usually done in textbooks, actually, okay? So the late time solution that you get is actually, again, the same as you get in ideal or dissipative hydrodynamics. So at late times, okay, this again goes to its equilibrium pressure and its viscous correction. And then if you really, so to calculate the evolution in between, even for the simple interaction, you actually have to solve it numerically. But what you find is that this somehow interpolates essentially between. So here we have equilibrium, okay, and we have first order hydro, okay, between this 0 pressure state at early times, okay, and the onset of hydrodynamics, and kind of the transition takes place on a scale where this is approximately of order 1, as you would expect from kind of just looking at the limits. So to note this down, okay, there's again a late time attractor here, okay, where the pressure is given by the equilibrium pressure plus viscous corrections, okay. plus, well, I can also write PL over E, okay, so PL over E would be PL over E equilibrium, and then I think the correction was 4 over 9 pi omega tilde, which you would actually do exactly the same way, okay, and this is then the interaction-dominated regime. Good. Maybe that's a good point to take a short break. Okay, good. Let's continue. And we've now seen this emergence of dynamical attractors in two different theories, so in kinetic theory and in hydrodynamics. And actually, there are some important remarks regarding this, right? So sometimes you just hear attractor, attractor, and this is why hydro works and blah, okay? But actually, okay, what have we actually found? Okay, what we have found is that there are fixed point solutions, okay, for different theories, and for different theories, they also look different, right? The Israel Stewart attractor at early times was just unphysical, okay, whereas in kinetic theory, okay, we get a attractor which has reasonable physical properties and that we can actually use. Okay. The other thing we said is that, okay, the emergence of these attractors is related to some partial information loss. In this case, we saw, okay, what actually happens is that the phase space distribution gets squeezed in the longitudinal direction. And in a sense, this is fortunate for us, okay, because we can learn something about the longitudinal pressure, and that's what we need to compute the work that's done against the expansion. So to kind of propagate our energy momentum tensor, okay. Does that mean that the system in any way loses more information? No, right? There are really also other properties of the system, like the transverse momentum distribution in this case, okay, which are completely unaffected by the fact that the expansion sets in. Yeah? So the fact that there's some information loss is due to the expansion, but the expansion by no means erases somehow all of the memory. Yeah? There are really also other quantities that really retain information about the initial condition, essentially all the way until the system thermalizes. An easy example is, for instance, consider a system of quarks and gluons, and you look at the relative fraction of quarks and gluons. Now, if you just expand, the expansion doesn't change anything about this, right? But you need interactions to convert sort of particles of different species, okay? So this is somehow, you know, something to really keep in mind, okay? And the other thing that's to some extent a little bit special about this Bjorken flow is that the reason that sort of this works so well in Bjorken flow is that we have really this very, very strong expansion rate at early times. Okay? And so for this reason, okay, I find it entertaining to also look at dynamical attractors beyond Bjorken flow. Okay? Okay, and so if you knew everything I've taught before, this you certainly don't know because this is not published yet. Okay, so don't scoop me on this, right? Okay, good. Okay, so throughout our derivations, okay, we have always worked with some essentially arbitrary scale factor, yeah, by which.
Because you mentioned this fact that there is this unphysical of the hydrodynamic attractor.
Yeah.
What concerns the later time? So the later time attractor, what one would like to see is that there is a convergence of the two attractors.
And this one sees, of course, yeah. And that's actually so. Okay, that's what we will find here, actually. Okay, that generically, okay, there is an attractor. Generically, these attractors agree between macroscopic and microscopic theories, but they don't emerge early, they emerge late, okay? And they emerge essentially after all transient excitations have decayed, and that's actually the conventional picture you should have of, you know, sort of applicability of macroscopic description. I would rather say in Bjorken flow we somehow get lucky that for the particular thing that we care, the expansion helps us, okay? Good. So what we're going to do here is, I don't think we can realize this in nature, okay, but we can entertain this thought experiment, okay? And so what we're going to do is now that we consider kind of a different variation of our metric, or of the scale factor, okay, whereby we, instead of sort of having this expansion, which is very rapid at early times and then slows down, okay, we're just going to periodically shake our system. Okay, so we're going to expand and contract our space. Okay, so we take a scale factor A of, and I'm just going to write T now. Okay, doesn't matter. Okay, I can call this T from now on. Okay, which has some amplitude alpha. Okay, and then it has a sinusoidal oscillation. Okay, sine omega t. Okay, and I want to set this up in a way that my system is initially kind of in equilibrium in Minkowski space, and then I start to shake the space. Okay, so that's why I put a heaviside theta function over here. Okay, and so in principle there's two parameters now I can control. So I have this alpha, which is the magnitude of this metric perturbation, so how much I expand my system. Okay, magnitude of the metric perturbation. Okay, and then I also have my frequency omega. Okay, so well, this is the frequency, but essentially what this really does is it controls the rate of expansion that I have. Yeah, so if I compute A dot over A, which is the expansion rate, then I take a time derivative. Okay, so what I get is what I get is a derivative. Okay, so it turns out, okay, that so first we should think about, what can we expect. Okay, so there is a regime, okay, where we would expect hydrodynamics to describe the response of this system. What do I have to do for this? So when would you expect hydro works well to describe some situation like this? I start in equilibrium and then I start shaking. What do I have to do with my shake? I mean, how has my shaking have to be? Yeah? Yeah, basically it has to be slow and weak. Okay, so basically alpha has to be small and the frequency has to be small, and by the frequency being small we mean frequency in units of the characteristic timescales of the system, so let's say in units of tau pi or so. Okay, so in principle we expect the hydro regime, okay, where alpha is small, okay, and somehow let's say omega tau pi is also small. Okay, good. Now what's cool about this is, okay, you can, in the regime where alpha is small, okay, you can solve this. You can solve this in hydro, but you can also solve this exactly in kinetic theory, in the RTA, and this you will do in the exercises, okay. Since I only have half an hour and you have an hour, okay, I will only do it in hydro, okay. And it turns out the solutions are exactly the same in that case, actually. So this is an example where Israel Stewart hydro actually describes the full microscopics of kinetic theory in this regime of weak amplitudes, but in fact arbitrarily large perturbation frequencies. Okay? And we'll understand why. Yeah. No. No, not at all. This is just, right? I mean, because now we're expanding and contracting, right? So we just want to set up a different problem, basically, yeah? To understand better what's happening, okay? Yeah. Okay, so we can try to solve this in Müller-Israel-Stewart hydro, okay? And that is not too hard to do, okay? So basically we just make use of everything that we have derived so far, okay? And I mean, what do we care about here, right? And what we care about is we are doing this anisotropic expansion of the system. In principle, we could look at heating and cooling and so forth, okay? But the more interesting question is, what happens to the longitudinal pressure in this case, okay? So we can directly just look at what happens with this pi eta eta, okay? So, and I'm too lazy to write this as pi eta eta the whole time, so I'll just write it as pi, okay? So what do we have? We have our usual MIS relaxation equation for the shear stress, okay? And so the way this looks is that on a time scale of 1 over tau pi, okay, this thing will relax to its Navier-Stokes value, okay, and the Navier-Stokes value we have also calculated, okay, this was just minus 4/3 eta times A dot over A. Okay, so good, in order to solve this, I mean, you already see this is not going to be terribly difficult, okay, but we're going to learn a lot, so these are the best things to do, okay. We need A dot over A next, okay, so let's calculate A dot over A, okay. So in principle, we take here time derivatives and everything, right? But we are interested in the regime of small alpha, okay? So let's write here, we do this for alpha much less than 1. I said this in words, but I'm going to do this approximation here, okay? So then if I take a time derivative, I get alpha cosine, alpha omega cosine, okay? But then I have to divide by A, okay, but because I already have 1 power of alpha, I can just set the scale factor itself to 1, okay. So if I do this for alpha much less than 1, okay, this is basically just A dot, okay, and this is the same as alpha omega times cosine of omega t, and I should retain this theta function here, okay. So let's plug this in, okay, and for convenience, I'm going to multiply the equation by tau pi, okay, then things look a little bit nicer behaved, okay, so I multiply this by tau pi. I also bring this over, okay, then I have pi plus tau pi dt. This I can write as 1 plus tau pi and the partial time derivative acting on my stress, okay. And you see why I'm doing this, okay? So this is now given by the driving term. The driving term, the tau pi I've multiplied over, is just the Navier-Stokes stress. So this is now just minus 4/3 eta, and then I have A dot over A, which is alpha omega cosine of omega t, okay? So in principle, this is now very simple, okay? So I get, I mean, this is a first order linear differential equation that is inhomogeneous, okay, so this is something you can solve in closed form, and I think you do this in the first or second semester of undergraduate studies, okay. Good. This is not what we're going to do, okay, but so you can also solve this by Laplace transform or however, okay. We're going to look at this somehow slightly differently, okay, because then we can connect this to some other insights that people have done, okay. We can look at this essentially by Fourier analysis, okay. Now that's not a good technique principle to solve a differential equation. You should rather do a Laplace transform, okay. But we get away with this here, okay, because then essentially we have on the left-hand side something that describes the dynamics of the system, and on the right-hand side something that describes the way that we drive our system, okay. Because this is going to become I epsilon in the next step, okay? Good. Okay, so now instead of solving this directly, okay, let's solve this by Fourier analysis, okay? So solve this by some kind of Fourier analysis, okay, and then in doing so, of course, we lose memory about the initial conditions. That's the standard thing, okay, but we can restore this at the end, okay? And so what do we do for this? Okay, in principle, we can write, I mean, we say that, okay, our scale factor now is some superposition of harmonic drivings, okay? So I write it as a frequency integral, okay, the omega over 2 pi of some amplitude in frequency space times e to the minus I omega t, okay? And so if I do just the Fourier decomposition of what the scale factor actually is, okay? Well, then I have to insert here, so I have to invert this, I guess, right, yeah, so I have to invert this, okay, and calculate this with the form of the scale factor that we have, okay? I have to get the theta function, I have to introduce an I epsilon. You know about this? I epsilon prescription, yes, right? Good, okay. So this is not so important, okay, so we'll come back to this later, okay. Okay, so I get I guess plus here, yeah, okay. So we get something where the frequency is equal to omega, another thing where the frequency is equal to minus omega, right? So these are the two frequencies that we drive in our Fourier analysis, okay? Yeah, and the poles in the complex plane are shifted to the lower half plane to generate us this theta function, yeah? No, I mean, I just do the Fourier transform with the theta, right? And then I introduce the epsilon for convergence. Yeah, but I'm not going to need a dot. Okay, so because a dot I do here, right? So a dot of omega, okay, is just minus I omega a of omega. Okay, good. So now we can take this whole equation in Fourier space, okay, and basically, okay, let's Fourier transform this whole evolution equation where here we still have our a dot, okay? So what do we get? So of this MIS equation, okay, so what do we get? Okay, so we get 1 plus tau pi dt, but dt is just minus I omega, so we get 1 minus I omega tau pi, okay, times pi of omega is equal to, okay, and then now we just have, we have 4/3 eta a dot because a is approximated as 1 in the weak amplitude regime, okay, so we get plus 4/3 eta I omega a of omega, okay, and so now we can immediately determine what is pi for a given a. We just divide by this factor here, okay. More formally, okay, we can actually, so now we have solved this for a response to, so okay, we find, okay, so pi of omega is 4/3 eta, and then we have I omega over 1 minus I omega tau pi, okay, and then here we have an arbitrary amplitude a of omega, okay. So what we see is that, okay, now we don't really have to drive this periodically, but we can do kind of a mixture of frequencies or any frequency, okay? Then what this tells us here is that here we actually have a Green's function, okay, for how our system in Fourier space responds to an arbitrary drive. Okay, so this is a Green's function, g of omega, and so formally this would be defined by taking a derivative of the shear stress with respect to the metric perturbation that you do. Okay, good. So now we can take this back to the time domain. I mean, we want to see what happens as a function of time, right? That's where we always saw attractors so far, okay? And this is now kind of where we start to learn about the physics, okay? So if we take this now, okay, so if we take this now back to the time domain, okay, then we can compute our pi of t, okay, by doing the inverse Fourier transform, okay. So what we do is we do the integral d omega over 2 pi, okay. We take our Green's function here, yeah, and we multiply our perturbation a of omega, okay, and have the Fourier phase e to the minus I omega t, right? So we have a linear response to some perturbation through a propagate, okay? Good. Now, how do we do this, okay? And so this is now, okay, so this is now the standard thing that you do, right? You do this by means of complex contour integration, okay? So in principle, what we have to do is we are integrating along the frequency, along the real frequency axis, okay? So this is the complex frequency plane, okay? So this is our integration contour if you want so, okay? And now we have to see how to close this contour to make use of the residue theorem, okay? So how we close this contour is given here by this exponential factor. I mean, this you all know, guys, right? but it's probably just been some time. Okay, so you have to see that the sign here is exponentially decaying, right? So if time is negative, okay, then it is I omega times some positive thing. So you want to have positive imaginary part for the omega to make this imaginary decaying. So for negative times, you close on the top. Okay. So this is how you close for t less than 0. Okay. And for positive times, you close the thing in the bottom. Okay. So you close like this. Okay, good. So now, why am I doing this like this? Okay, because now what you see is that when you compute this, okay, the only place you're picking up something is to the singularities what you have of your integrand, right? And the singularities of the integrand can come from two places. They can either come from the Green's function, okay, which encodes somehow the intrinsic response of your system. So this is a property of the system, right? So this tells you, how does in this case, your Müller-Israel-Stewart equation respond to something, okay? And of course, from the singularities of the driving, so these are just the two driving frequencies that we have, okay? So if we look at the poles, okay, then the poles are located. Let's write them. So this and now this is why it's important that the poles are shifted. So the poles of the driving frequency are here at plus and minus omega and shifted infinitesimally to the lower half plane. Okay, that's the theta function. And then we can look at our Green's function. Okay, so where does this have a pole? So this has exactly one pole, okay, and this has exactly one pole, and that pole is in the complex plane, so it's on the imaginary axis, it's at minus I over tau pi, okay? So then, good, so then what you have to do, right, okay, so you look where the poles are, right, you calculate the residue at the pole, you multiply by 2 pi I, and you sum the thing up, okay, so now we can see what happens. Okay, I'm not going to do this in small steps, okay? But basically, if I pick up such a pole, okay, what I get is I get the Green's function evaluated at that frequency. I get frequency omega being equal to plus or minus capital omega, so I get the combinations of cosines and sines, yeah, with some amplitude that is determined by the Green's function, okay? Now, in addition to this, what I get is from the pole of the Green's function, okay, I get a contribution where omega is equal to minus I over tau pi, okay. So this results then in exponential decay of minus t over tau pi, okay. So then you can add this together, so we get a sum of cosine, sines, and exponential decay, okay. So we get, I told you this in words, I wrote a little bit more here, okay. So the answer that you get is you get minus 4/3 eta omega alpha, okay? So this is not surprising, this is just the amplitude that's up front, okay? Then you get a term which is cosine omega t, okay? Then you get plus omega tau pi sine omega t, so these are the oscillatory terms. And I think I have to erase my sketch here, unfortunately. Okay, so this is all what comes from the concrete form of the driving. And so basically what this means is this follows the driving with some amplitude. So here's going to be a denominator also, and the phase shift. That's the normal thing what you get for these driven oscillatory equations. Okay, but then you get also the other pole, and what the other pole is subtracts. So it has this kind of behavior, e to the minus tau over tau pi. Okay, and then overall, there's an amplitude which is 1 over omega squared, tau pi squared. Okay, so this is just evaluating this integral. Now, if you look at this, so this is pi of t, okay, is this. Now you can look at what, so we should analyze this now. So we have oscillating, so we have some oscillation that follows the driving with some phase shift and some amplitude that depends on how fast the frequency is in relation to the natural driving, okay, and we have a term that is initially there, but then exponentially decays, okay. Now, if you look at this, okay, say you go to t equals 0, then the sine doesn't contribute, the cosine is 1, this is 1, so your initial stress is 0. Okay, this is because we solved this by Fourier transform. Okay, if you want to add somehow the actual initial condition, okay, so this would also exponentially decay. I mean, this is relatively easy to see from just looking at the differential equation. Yeah, you just solve the homogeneous differential equation and you get a decay with minus tau over tau pi. Okay, irrespective. I mean, yeah, for any initial for the initial condition. Okay, so now let's analyze what this does. Okay, so what we see is that at early times, okay, we have these transient terms, okay, which are these decays on a time scale tau pi, so this guy here, okay, where we lose memory about initial conditions, okay, and, well, this just kind of goes away, okay. So we see we have a decay of transients, okay, which go as e to the minus tau over t over tau pi, okay, and on this time scale we also have sort of memory loss about initial conditions. Yeah, but now look what the time scale here is, right? The time scale is tau pi, okay, and the transients that show up, yeah, are actually, so where did we get the transients from? The transients come from the poles of our propagator, yeah, of our retarded propagator, so from the singularities of our retarded propagator. In this case, we had exactly one singularity, that's why we have one transient which decays precisely like that, okay, and that is the property of the Israel-Stewart theory, okay. So what the Israel-Stewart theory does, that's what we said, right? It's, okay, we introduce some transient dynamics that makes us go to first order hydrodynamics, okay, and here this is exactly what we recover, right, as we see that, okay, this transient shows up as an excitation mode of our system, okay, and if it's initially excited, it decays, and then I find some long-time behavior. Okay, so in this case, we have this transient dynamics for times that are small compared to tau pi. Okay, and so in this case, time is just, so this means time much smaller than tau pi. Okay, and at late times, okay, t much larger than tau pi. Okay, what we find is that we find an attractor, so where we can basically just throw away these exponential terms. Okay, so here we have an attractor, which is just given by dropping this term. So you want me to write this down again? No, right? No, good. Okay. Now, what is interesting is to also look now how this solution depends. So we said in principle we expect hydrodynamics, okay, to be good in a physical theory, okay, for weak amplitude and sort of slow shaking, right? Now, what we didn't consider so far is what happens when we shake slower or faster. So we didn't really talk about very much about varying the frequency at which we expose our system to this oscillation, okay? So let's analyze, so let's stick on the attractor, okay? So let's wait until the transients have decayed, okay? And let's analyze the frequency dependence, okay? And this is actually relatively interesting. So the frequency dependence, okay? So if we look at the attractor, so I drop the transients, okay? And I take the limit that omega tau pi is small, okay? So if omega tau pi is small, then I can drop the sinusoidal term here. This denominator just becomes 1, okay? So what I get is I get 4/3 eta omega alpha, okay, times cosine omega t, and there's an overall theta function here that I didn't write. Sorry about this, okay? Yeah, okay, and so this expression looks familiar, right? This was exactly what we had what we had written as the driving of our equation. So this is nothing than just the Navier-Stokes solution, okay? So indeed, right, if we shake slowly, okay, then the fact that, you know, you have to always relax first to the Navier-Stokes value doesn't play a big role, right? Because we don't lag much behind, so we converge to this Navier-Stokes solution. So first order ordinary hydrodynamics, okay? Good. Now, the thing is though, right, that the fact that we have this dynamical attractor, this is irrespective actually of the fact how quickly we shake our system. Yeah? I mean, this is something that always happens after the decay of transients. We always go to this solution, and this solution actually persists even if we shake our system very quickly. Now, what do you expect for, I mean, physically, what do you expect for the system to occur if you shake it very, very quickly? Yeah? Exactly, right? So what actually happens is that, I mean, that's what you expect, right? That the system can no longer react to when you perturb it very, very quickly, okay? Yeah, and indeed, this is what this solution features, okay? So if you look at now, you make this large, okay? First of all, the sine takes over compared to the cosine, right? But then actually the amplitude of the perturbation also goes down, okay? Because you're suppressed by this, okay? So in opposite to the Navier-Stokes solution that actually blows up if you shake it very quickly, right? Then the stresses here become larger and larger, okay? You find a completely different behavior, okay? Where actually the stresses are reduced, okay? You go into a regime where the system no longer responds, and this is indeed now actually accurately described by this Israel-Stewart relaxation equation, okay? So you can sketch this a little bit more, okay? So just to give you an idea of what this looks like, okay? So you can look at the ratio of, say, pi over the equilibrium pressure, and you can plot this compared to the Navier-Stokes solution, okay, for different driving. So if you drive very weakly, okay, then, well, first of all, how does the Navier-Stokes solution look like? Well, the Navier-Stokes solution plotted as a function of the Navier-Stokes solution is a straight line, right? Okay, and you can have positive and negative stresses because you're expanding and contracting. So A dot over A changes sign. Okay, and so this is kind of when you're at one end, and this is when you're at the other end of the spectrum. So as a function of time, you kind of oscillate back and forth if you just do Navier-Stokes. Okay, now if you look at what your Israel-Stewart solution does, is it has some decay of transients. Okay, but then it goes to this solution because you have this cosine and sine terms. You have sort of a slight phase shift in the in this oscillation, and this leads to kind of some kind of tiny ellipse in this stress around this. Okay, so it'll look like this, and different initial conditions go there on a time scale that is given by 1 over tau pi. Yeah. Now, if you make this larger, okay, so you can plot the same thing. Again, as a function of the Navier-Stokes, okay? Then Navier-Stokes always looks the same, okay? But now, what tends to happen is that the response gets weaker and weaker, okay? And the phase shift gets larger and larger, and so actually what happens is that kind of this ellipse starts to somewhat tilt, okay? Again, you still have an attractor, okay? Once your transients have decayed, okay? But now the attractor no longer looks like your Navier-Stokes solution, okay? And eventually, if you make this very large, what happens is that actually kind of the Navier-Stokes stays the straight line, but this tilts by 90 degrees and sort of shrinks to a point eventually as the system can no longer respond to this. Yeah? So one of the things we learn here in doing it, we learn two important things. Okay, one that we learn, so it's sort of natural to expect emergence of attractors, but only after all the transient excitations of your theory have decayed. Okay, and then if you ask this the question for a concrete system, you have to ask what are possible transient excitations that I can have. Okay, and the second thing that you learn is that somehow the hydrodynamic theories that we actually use, okay, they are fairly advanced, okay, in the sense that they can not only describe the first order hydrodynamic limits and small corrections to that, but sometimes they are also very good in situations where we maybe wouldn't have expected it, okay? Good, I think with this I'll close, and if there are no questions, let you go to lunch.